Kaçtım hocam üçündür. Arka planda ama o bitince öbürünü değiştirmek gerekebilir abla.
Okay, so we are all set. Whenever you are ready, we can start discussing some quantum algorithms with you. I think we are a little bit already late, but there's a 10 or 15 minutes delay. I can start immediately if it is. Okay. Yeah, I didn't start. I'm asking if I should start. Okay. So welcome. Thank you very much for joining us today. Today I'm going to talk about quantum algorithms, how to implement them on practical situations, and just setting the scene for the basics of quantum programming. Actually, it's a little bit strange at first sight because this call is dedicated to photonic computing, but I'm going to talk about some quantum algorithms that can be run on superconducting circuit-based architectures. The reason for that is currently we have limited in our options. There are very few photonic computers available for cloud service. Therefore, we are going to use IBM's more popular, which is more popular choice, IBM's quantum computers. So we are going to use this, but the ideas, concepts, and even QSIT is in a sense agnostic. It is hardware free. You can implement it in different systems. Once you learn these concepts, you can easily convert your codes to PennyLane. You can convert codes to other languages that can be run on different quantum computers. Okay. So the purpose of today's lecture is to prepare you for the evening. Hopefully, when you go back at home, you will install QSIT and run some quantum algorithms on your own, and maybe do some homework that I'm going to assign. And we can continue discussing while I am here in the rest of the days. Okay, so QSIT is currently available with versions greater than 1. Earlier versions are not easy to use with the new version, so it's better to just start with QSIT 1.0 or 1.2, which is the latest version. So maybe I don't know how to do this. Okay, it shows like. Oh, what I should do? Okay, great. So I assume everybody knows Python, yes? So if you are familiar with Python, it will sound you more computer language rather than being an animal. So I hope at this level, it sounds more quantum programming language, also suitable for quantum programming as well. But also, you know, in Python that you need an environment. If you visit some vivariums in some zoos, different Pythons live in different vivariums, right? So you need a different dedicated environment to run your Python codes. So I'm going to make some assumptions for your specific Python installation, okay? So I suggest that when you go back home, if you don't have it, and if you have limited space like in your laptop, then it's better to use an environment manager called Miniconda. Okay? Anaconda is a huge snake, yes. I don't know why it is with those snakes. But this is Miniconda, and it only takes about 500 megabytes after installation. There is a better, more powerful with lots of packages, everything if you want, the huge snake Anaconda. It is about 3 gigabytes. But if your space is valuable, let's stick with Minicom. And here you can download it from this link. And when you go there, you can also choose your special system. That is your type of PC. Okay. Well, in an ideal world, we can assume everyone has access to Mac computers. They are expensive, but let's assume that this is an ideal world and everybody can access a Mac computer. Okay. So I was lucky, I got one from my project. So I hope you have some access to them. It is easy to install them in Mac, but I think if you have Linux systems or if you have MS Microsoft systems, again, you can look at this link. They have special instruction set, but here I'm going to use Mac. Okay. So also I am very not so hardcore programmer, so I don't like terminal too much. But if you like, you can do installations in terminal with lots of options. But if it is sufficient for you, just focus on what is quantum algorithms. You don't want to deal with lots of technical issues. Just go for a graphical installer for your particular system and choose it. Then just follow the logical instructions and install Minicom first of all. Okay. So, in my world, everyone has a Mac, but my family also wanted to use my Mac, so I shared it with my daughters, Daphne, Michelle, and sometimes my wife. So I have to use carefully my special location of installation. So be careful if you are doing the same. So choose your installation location and also choose your chipset. I use Intel. If you use AMD, you choose a specific chipset. And after those points are taken care of, just go and install your system. Okay? And this environment is very good. Now, from the Minicom is in our system installed, we also need a place to write our codes. Okay? So again, this is a very personal choice. But I like this ESC, which is Visual Studio Code. Again, you can download it from here. Okay? I will share my slides with you. You can find this links there. And here it looks there's a nice color codes and some extensions for your program that helps you debugging, etc. So this is a common personal choice. Let's go ahead and install it as well. All right. So after all set, so one thing I like about this VSC is that I can open my terminal within my code. Okay? So I don't have to go back to my operating system and start the terminal. I can just read by pressing some button on top, and then a terminal appears here. Okay? So why I need a terminal? Because in terminal I have to create some environment. Okay? This is what Minicom is for. After you install Minicom, you can manage different debuggers for different Python titles. Okay? So here, my dedicated environment is our false loop. And after you create this environment, you activate it. After you finish your session, deactivate it. Okay? So everything will be consistent by this. If you don't do this, if you don't want to use formula, you will see there is a base written here. After these steps, this base will change to false code. Okay. Time to install our qscript. And for this, we need a Python installation manager program, which is PIP. Okay? So, if you don't have it, again, you can install it from your command. After that, you can use PIP to install qscript. And here you don't have to worry about which version you need. You can go for earlier versions if you need them. But otherwise, it will install your 1.2. Okay. All right. So this is not a complete installation. qscript comes with a lot of scientific packages, but still we need a few more for comfort. We install this PyLatex because we love LaTeX. Yes, it is our scientific language. Alphabet. Then we also install this IBM runtime. If you are lucky, you can access IBM computers in a reasonable time. And you also install some Photonic package. All right, this looks a lot, but it doesn't take too much time. Okay. All right, so suppose you did this all at home this evening. How to test if everything runs correctly? Okay. So open your programming editor. In my case, it is a VSC terminal. Okay. Then here in the terminal, just go to TÜBİTAK. Okay? So once you run your VSC, it will ask you what you want to do, and you will say that you will choose among the options the TÜBİTAK notebook. Okay? So TÜBİTAK notebook has some cells. It's very similar to mathematical and other mathematical software, where in the cell you type something and then shift enter to execute the command. All right. So in your TÜBİTAK, you can choose a logical name for your file. Then always make sure that you are working in the correct kernel. Okay, the kernel name should appear on the top. Okay, so currently it is Python, but if you press on it, you can choose the correct kernel so that you are working in your active environment. Okay? So everything will be consistent because all the packages you need are within this environment. All right. Then the first command we will type will be to import QC. Okay? And once you import it, you can check the version, and you should see the correct version. Okay? And after these steps, you are good to go. Now, last thing, remember we installed an IBM runtime platform, which is this IBM runtime. Okay, this is where we access actual hardware, actual quantum processing units. Okay? There are several of them. And I am cheap, I just use the open version, free. Yes, so I have 10 minutes of being quantum in 1 month. So if you want to pay $1 or something per 10 seconds, then you can go to premium. But it's a very good idea because it's getting more and more delays nowadays to run a quantum program. You have to wait a lot of time. Okay? If you are poor, then rates are going fast. Yes. Anyways, so here from QScript runtime, IBM runtime, you import to runtime service. Okay. So this code can be copied directly from this cell. If you press these dots, it will ask you whether you want to copy your token or if you want to copy your activation code. Activation code is this 3 4 lines. So here you will see a list of letters and numbers, which is your token. I changed it here. And you have your channel and your program if it is open or premium and so on. Okay? So once you do this, you don't want to do it all the time. Yeah? So you just save it. And whenever you use your active, in this case my false school active channel, I don't have to type this again. I will always access the quantum computer whenever I want. Okay? These are the open public quantum computers, and you can see the reasonable number is 1.127. This eagle is very, very famous. After the eagle, they say we now are in the utility era. We can do something useful with quantum computers and so on. So you can access them. Let's say you hope to access them because really it is getting very long time waiting time. So you can choose your backend for your quantum processing unit from here, but there is also a command which you can use to choose the least busy version. So there's the English version command. You can type, please give me the least busy computer. Yeah? Okay. So I usually work with this. 127 months, the waiting times are reasonable, at least. Yeah. So you can specifically name your chosen system, but I rarely do it. It is sometimes better just, usually better just to type, give me the least busy one. And of course, all these different architectures have different connectivities, different number of qubits, different noise properties, and so on. So if you need a specific information about the computer, you can ask about its properties. Once you put that here, it will list a lot of attributes. So you can choose which information you need, and then just press on it, it will give you the information. Okay. So in the QScript web page, and also in this GitHub page, you can find more information than you need. You can even contribute as a developer. So this is an interesting kind of language, not similar to, let's say, C, Fortran, etc. This is always under development. So you should feel like a bit beta testers always, yes. And always imagine that you are using your computer, somebody comes, change your hardware while you're programming. This also happens, lots of maintenance, lots of changes in the hardware. One command works 3 months ago, it changes, it cannot work now. So be ready for this. It's not a pain, it's kind of joy. You are part of something new, and you can contribute to development as well. Okay, so if you have any questions about installation, I will be around. Of course, the questions will appear when you try to install. You can ask me. But I want to continue with more conceptual information. There is no whiteboard or anyway, I can write something if you have any theoretical questions. But I don't know how to do it. Maybe I will try to describe if you have theoretical questions. Okay, so in this part, after you install QScript and make sure it works properly, you get two options. You can either run your codes in some simulator or a fake backend, or you can use it in a real hardware. So we will give a very simple examples how to do this. And after that, we will be ready to discuss a quantum algorithm. All right. Well, let's also discuss if you are a quantum programmer, how you would approach a problem given to you. Yeah? So given problems, most of the time they will be classical. Okay? Like a traveling salesman or optimization of some financial stock market or through some logistics. Yeah? And in this case, there is a big gap between problem and the hardware. And what you should do as a programmer, you should, that is why you need some physics education or some understanding of quantum mechanics to be a quantum programmer. Okay? So what you do is you use your physics knowledge to map the problem to some quantum metric format, which is basically, in our case, operators. Yeah? In quantum mechanics, when Heisenberg first founded, Heisenberg loves linear algebra. He even invented matrix products again, if you know the history. Yeah, so quantum mechanics is basically linear algebra. Yeah, there are operators and operations of these operators on some vectors living in strange spaces like Hilbert space. Then architecture of these operators in this case are plotted like a music note, like a music composition on a circuit. Okay? So we shall see how to do this. Then the idea you have or the map you have found may be not directly within the architecture. Okay? Suppose your map is a linear chain of qubits, but they may say that, okay, in my hardware, in my photonic computer, in my ion trap computer, in my superconducting computer, I have only triangular lattice. And so then you have another issue. You have to map again or transpile again your code into the available architecture connectivities. Okay? So this is known as optimization or transpilation step. This is where the real art is. Okay? So the real physics start, and this is we don't have any systematic answer. So one programmer will be better than the other because he or she may have more experience with this particular architecture. He may have better insight and so on, or maybe recognize some symmetries in the problem and so on. This part is art, where one people will be different than the other. This part is where you simply run your circuit, evolve in time, a Hamiltonian evolution in quantum mechanics. It's an open system subject to lots of noise. Okay? So here you choose, instead of being acoustic, you choose to implement your code in a specific hardware. And therefore, every hardware has its own problems. In the case of photonic computing, you have learned maybe photon loss is a big issue. Yeah? So you have to do something at this step to mitigate this photon loss. Or if it is superconducting computer, qubits are very close to each other, they can do crosstalk. Okay? In this case, what you should do something to avoid this crosstalk. And in every computer, there is a photo detection or readout stage or some measurement stage, like quantum state tomography. Again, it has a lot of errors. Then, even in the reset, when you assume all the qubits are perfectly reset to their initial zero state, 0 qubits, yes? What happens if one of them is flipped unintentionally? Then again, there are lots of errors. So all of them are handled at this stage. And you will get the result. Yeah? So this is the problem. Yeah? So if you don't know the physics, so I think some clever guy, Einstein or maybe somebody else, said that it is better to guess the result first. Yeah? So that if you find the expected result, you will feel comfortable. If you don't find the expected result, you will be surprised. And then you will revisit your assumptions and maybe using this feedback, improve your model. Yeah? But always guess your result and make some post-processing against the expected issues. All right. So if we want, let's say our problem is now not a classical one, but a quantum mechanical one. Because for many quantum mechanical applications, one of the important resources is quantum entanglement. Okay? And the simplest entanglement state is a 2-qubit entangled state. There are 4 of them, known as bell states. And we want to generate at least 1 of them. Okay? And here, to map this problem to a circuit, the answer is known. Probably you will hear this somewhere in the school. You need an Adenoid gate, which basically puts a given single qubit state in a superposition state. Okay? So here we assume that we perfectly reset both qubits in their lowest energy state, in the ground state. You can do this by lowering the temperature relative to their energy gap. Okay? Or you can use some pulses, microwave pulses, for instance, to split them to their ground state. So they are perfectly reset. Let's assume there is no error here. And these are ideal also. We don't consider any error correlation. So after the superposition, this is a control dot gate. So depending on this control qubit, it will flip or not flip. It's a control quantum interdynamics. If you flip or not flip this qubit state, it will either excite or will not touch it. Okay? So if you do linear algebra, map these operations to matrices, define a vector here, run the linear algebra, you will find that you will generate a state 0, 0 plus 1, 1, normalized by square root of 2. Okay? So this nice picture here is thanks to one of these packages we have installed, so that you can use this MPF for this nice plot. But if you don't bother, you can also see this control marking as a control X state. X is the single qubit state flip operator, and this other marking, it shows more explicitly the letters of the qubits. Okay? And to write this in QSIP, we first of all import quantum circuit from QSIP. Okay? and say that I only need 2 qubits, and there is no classical register, just 2 quantum qubits. Okay? And at the quantum Hadamard gate, the 0th qubit starts to number qubits from 0 to n. And that means you add this to your quantum circuit. And the next sequentially adds a controlled NOT gate. Remember, this is explicitly showing you that it's a controlled X-state, basically. Okay, so you have Cx. And this is the control qubit. 0 is controlled if it is depending on 0 or 1. You either flip or not. So the target qubit or the state to flip is in the second qubit. Okay? All right. So this is just drawing the circuit. All right. In the next step, or the second part of the first step, quantum mechanics is all about observables. So you should know what are the interested observables are. Observables are permission operators. Their expectation values are real valued, and they are measurable. There is a more general theory of the post-operator value mergers and so on. And we are not going to touch that yet. Just assume that this is some operator, permission operator. Okay? Then if you have 2 qubits, we have a combination of different observables. So one of the methods to characterize the quantum state is so-called tomography. Okay? Tomography, it's medical tomography. You go and just turn on some probes around you and look at you from different angles. Okay? So let's say X, Y, and Z are our coordinate axes, and I want to look at my quantum state from different axes. And for this, Z and X are sufficient. In this case, we don't need Y. And I is just identity, it means do nothing. Yeah? And these are actually Pauli operators. In the optics, if you want to do optical analog of that, Pauli operators change to Stokes operators. Stokes operators are polarization operators. Yeah? Whether you have circularly polarized right and left, how they are imbalanced is measured by Z. And this is right and left circular polarization field. Okay? In the case of qubit, Z becomes a phase operator. It changes the phase of the qubit. And X becomes a flip operator. Okay? And in this notation, in qubit, we don't put a transfer product notation. Normally, if you have 2 qubits, you have 2 qubit qubit space. So these operators belong to different spaces, and therefore we need tensor product. Okay? And these are observables. Why we choose them? Because if the state is in the band state, they execute a certain value. So I can use this tomographic method, looking at different angular Pauli operators. I can characterize my state, whether it is a band state or not. For instance, this is 0 qubit and first qubit phase operators in tensor product. If this is a band state, it should always give you 1. Okay. So you can do the math, write this band state 0, 0 plus 1, 1. And write all these operators here and calculate the numbers. And this will be your benchmark. After you run your circuit, if you get these numbers, then you say, I successfully created the band state. Okay. Do I need to explain any terms? So, okay, this is an interesting idea actually. So, what do we do in this? Connotations are just letters, yeah. So these are strings. So one might think that from physics, I like to write a Pauli operator sigma x, sigma y, sigma z. Yeah? But in concrete programming, it's nice to be able to call them zx, which means I can do algebraic operations, string operations, cleverly to make my life easier. Okay? So instead of assigning sigma x and tensor products, etc., I just write letters here. And in QST, it recognizes that these letters that are these are actually operators. Okay? So I can feed in letters as strings to the QST, but it will treat them as operators. So you can quickly assign them to operators by a simple for loop. Okay? And this sparse means Pauli matrices have zeros. Especially if you do tensor product, you will get a large matrix with lots of zeros. So you don't want to store a lot of information unnecessarily. So sparse matrix operations, if you are familiar with MATLAB, it makes the computation much faster and less resource demanding. Okay, so we are going to use first a simulator with the error-free, so we don't need optimization, and we have only 2 qubits. Again, it will be very fast. So we will do this step later. So to execute it, we have to choose a simulator, not a quantum computer, and in QSIT there is an AR simulator, and from its primitives you have different options, like it can give you output like a distribution function, because it is all statistics when it comes to quantum mechanics, so it can make a distribution, or you can use it as an estimator. You can estimate the output of after experiment, what's the probability of certain outcome. So you will choose to here use estimator. Yeah. And we have to assign a job to our simulator, and here an estimation job. And this estimation will be output of this quantum circuit that we have defined before after we run. Yeah. But we have to run this because we have ZZ, IZ, IX, XX, 6 observables. So therefore we have to make our circuit 6 times more. So we multiply by the length of this observables array, which is equal to 6, or you can, if you want to change the number of observables, better just say that, which is the length. Okay. An estimator will estimate the expectation values of the observables. That is the result of measurements. Okay. And it will record the results in this job result variable. Okay, so this is the result. How to plot it? You use the standard matplotlib. Okay. And our data is the 6 observables. And we want to, this values means expectation values. Okay. So it is the expectation value of these operators. And we will plot the values for each data. Okay. And this is just some design of the plot. So let's look at this result. You can see this is the result of XX measurement and ZZ measurement. These are global 2-qubit measurements. And it will give you 1, while for the single qubit measurements, because I is INF operator, it will make some noise, but it will be in or average 0. Yeah? So we are somewhat successful to generate a real state as expected. Okay? Sure.
Does this expected value is same as what you shown for the tensor product of the expected?
Yeah.
Okay, so then what are the 2 inputs of that tensor product? Like in the previous slide, it was
the input depends. So we start with all the qubits in 0 state, run the circuit, evolve them in time. Then after 1 run, okay, this is 1 run means single shot. After single shot, we get some probabilistic values of these outcomes. Okay? On average, if you do expectation value, single qubit exactly should give 0, because if you put here bare state, you can easily calculate them. Okay? But if you run the experiment for single shot, this is only statistical average. Yeah? So in quantum mechanics, there is a possibility that this can jump to the okay. But the probability is very low. But there is a probability. But on the average, it will be on my hands, in my hands. Yeah. So this is on average. So in single shot, you can see many different results, even some minus values here. But on average, so I think this is the result of about 5,000 shots. So these are the definition of peaks and the operators if you want to do this calculation. Okay, so the question may be, okay, so this looks successful. There are 2 interesting observations. First of all, it seems the upper state is very correct. Yeah? It is perfectly fine. But lower single qubit measurements, there is a lot of noise. Okay? So this can be attributed to the fact that this global quantum entangled state is, when you do global measurements, is suffering less from shot noise. Okay? These fluctuations are called shot noise. From different bands of different bands, you get a different result. Okay? So different repetitions of the experiment will give different result. And if you want to reduce this and get the expected result, you have to send more and more repetitions and shots. And normally, for instance, this is in this comment, if you add this option, shots number, if I write here more than 10,000, I can eliminate the shot noise significantly. And then my device is working better, and because of the fact that it produces the state more slower. So if you want a best state in your device, if you sacrifice the waiting time, if you make your device slower, it works very well. So shot noise is not a big issue. By increasing the number of repetitions, you can reduce it. But why people are dealing with this and try to improve the shot noise and precision is, first of all, in measurements, it's an issue. And also the speed is sometimes, actually, most of the times, speed is important. So there are many papers you can see in the literature, single shot or few shot observations of the quantum entanglement and so on. Okay? All right, so if you want to run this in a quantum computer in the choice of simulated stage, I will write some IBM Brisbane or some other chipset QPU, and then run it instead of simulator on this case. For instance, here I think I chose IBM Brisbane, and it said that I have to wait 3 hours for this simple case, which I got in simulator in 0.1 second. Okay. So we say quantum computer is very fast, but there is a catch. Okay. So if you are patient, the operating time we can see is 12 seconds, even longer than simulation. So after you wait 3 hours, it will run the code estimated in about 10 seconds. Yeah? But it's still not that fast. So saying quantum computer is fast is actually not the correct way, as this demonstrates. Okay? The superiority of the quantum computing is not in the speed most of the time, but the superiority comes from the fact that you have to solve a problem not solvable by classical means. Okay? So when we discuss a quantum algorithm, we will see there is this situation. Okay, so if you this situation comes from the following fact: the scalability, or so how the quantum superiority enters as the number of the qubits increase, is critical. So we can generalize the band state from 0011 to N0 and 1 qubits. Okay? So this is an n-qubit band state, but it is a special name. It is called Greenberger von Zeidinger state, GA state. Okay? Why it deserves a special name? Because if you do the math of the quantum entanglement after the number of 3 qubits, things start to change. 2 important classes of entanglement appears. One of them is the W state, the other one is the GSC state, and they are not convertible to each other. And they are very distinct classes. If you go to 4 qubits, then you have bound and distillable entanglement. Again, they are very different. So if you go to multiple qubits, the character of entanglement changes significantly. And recognition also changes significantly. But from practical point of view, I can easily take my band state circuit and make a ladder of control X or control Y gates to generate this state. Whenever these guys see 0, it will avalanche zeros. Whenever these guys see 1, they will predict the states and make avalanche of 1. It is out of power.
Okay, use this microphone.
Okay. All right. So the problem is very same. Don't worry about this fancy stuff, but basically they keep adding more and more control X gates in a for loop. Okay, it's not a big issue. All right. So step 1 is again the map. In this case, we do some this nice arithmetic. Okay. So our observables will be too much. Yeah, if I also add the X state here, our observables will be too much. So I will only consider the Z state, this Z observable here, Z Pauli matrix here. And what I would calculate is as I said, you should have some vague idea what to expect. So if I go from 2 qubit to more and more qubits, I expect entanglement will be less. Yeah. Why? Because imagine my architecture is a chain of qubits. And in physics, we know that entanglement is a manifestation of interaction between the qubits. But in physics, we know there is always inverse square law of force. Some interactions decrease as the distance increase. Yeah. So therefore, the correlation between nearest neighbor qubits will be large, but correlation between this qubit and the qubit at the end will be very small. Yeah. So as a function of the qubit distance, I expect the entanglement should decrease, or this Z correlation should decrease. So I choose this as my observable of interest, but how to program it easily? Because I have n qubits, I would look at correlations between, let's say, first qubit and this particular qubit in the middle. And let's say between these two, all the other qubits I'm not going to touch, and they are observables of identity operators. And let's say there are k of them. Okay? So in alphabetic operations in programming, if you use a string and multiply it by k, that means you write this I k times. It's just alphabetic manipulation. Then put Z here. Then I have used k letters, 2 more letters, k plus 2. I have n qubits, and I reduce n by 2 plus k to find the remaining number of qubits, which I'm not going to touch, again assigned to identity operators. Okay? So this is a string. And from the string, again, I use my for loop to generate operators. Okay? This is the nice thing that I label file operators by letters. This is just making my life easier in programming. All right, second step is now somewhat critical. Here we are not going to do any art, just make a brute force and choose some runtime service, which is not going to use any simulator. Okay? And we will choose not a specific hardware, but let us use a hardware which is not currently busy. Yeah? So it can change during the calculation. All right. So this is an optimization level. We do not have the computer or IBM or we do not offer any insight, physical insight. So we just do brute force and just leave all the optimization to the hardware and the software. Okay? So they will do it. And we even are worrying that we will wait too long time. So we just write tier 1. It is the lowest level of optimization. Okay, so once this is done, okay, then this is the main issue here. So all these operators that I have strings of Z's and I's, okay, they are assigned from 0 qubit to n qubit. It was a chain in my mind, yeah. But if it gives me some least busy simulator, let's say with square lattice connections, yeah. So all these observables and qubit numbers will be reshuffled, okay. I could keep track of them if I know my certain hardware and optimize it myself. But if this is done by the system, it is better to also let the assignment of the qubits done by the system. Okay? So we write this step so that the qubit assignments will be done properly with the hardware layout and the layout in your problem.
The gate structure, why do you assume a chain structure?
It is just to develop a hypothesis. Just a hypothesis that I expect if the number of qubits will increase, then entanglement should decrease. So I just find that even if you use a square lattice, triangular lattice, eventually some qubits will be farther and farther from my first qubit.
For example, if you have a star connection, I mean,
then things might get better, yeah? So you can optimize. So maybe the result I will get, it should depend on definitely on the hardware. I may get very rapid decay of the entanglement, but in star connection, other connections, it may be longer lived. So in different hardware, I can get different results. These are important questions that are asked usually in the fourth step, in the post-processing, but it's important. Okay, so again, as we discussed, these connectivities are important. Also, symmetries in different connectivities you can exploit. To do this step on your own, but this is a way because you are just starting this business. Let the system do it first, and you can maybe choose the hardware and work on specific hardware, maybe in some just busy hours, and see if you can get improvements relative to system. Okay. Also, we said that there is a problem that once you go to the real hardware, even if you choose the optimal connectivities, symmetries, and optimize your system, eventually you will face errors. Because as you use the chip, especially more and more qubits, you're exposed more and more to larger and larger environments. Yeah? That is why our teacup is small. Yes? So we want it to keep warm as long as possible. But if you use a larger surface area, then you will lose more to heat. It's similar as you go to more and more qubits, this becomes a big issue. So there is several solutions, and one is that dynamical decoupling. Okay? So as I said, this is quantum circuit is basically Hamiltonian evolution. And ideally, it's a unitary transformation with reversible computing. Yeah? But it is non-reversible actually because there is always this environment. In the superconducting qubit, for instance, we have this 20 millikelvin temperature dilation fridge that freezes our qubits. But even this causes some decoherence or loss of quantum information. So what we want is actually to decouple this environment from your qubit. But I immerse my qubits in dilation fridge. How I can decouple it? The clever method is, let's get one more Hamiltonian, which is basically a microwave control. Okay, so when you look at this big dilation fridges, actually they don't have to be that big, but they have to get lots of little wires on each qubit to control them. That is why we have larger and larger quantum computers for larger and larger qubits. And these wires can send periodical signals. Okay? And these periodical signals can reverse the effect of the bad coupling. Okay? You can imagine like this. Currently, I am in an environment in terminal equilibrium. Why? Because lots of little molecules hit on my face. Okay? This is a chaotic environment. Okay? But if I make them periodical, then I can get a competition. So I can reduce the effect of one environment with respect to the other. So this dynamical coupling means if there is an environment you want to decouple, you choose a specific periodic pulse sequences to mitigate the effect of this environment and try to isolate your system dynamically. This XY, or I think you will listen some quantum optic courses from Jacob today, maybe also yesterday. So the basic interaction between light and atom, also light and metal, is dipole interaction. Okay? In dipole interaction, you have electric field and some dipole interacting. If electric field is classical, this is called semi-classical quantum optics. And in semi-classical quantum optics, we can use Basel classes, treating the dipole as a quantum object. And dipole is just a polarization. Okay? But polarization is then just a flip or transition. So whenever light comes, ground state goes up, or it emits again, it goes down. Yeah? This is X or flip operation. So therefore, you can encode the flip operation by a dipole interaction between a Basel class, and you can do it periodically. And if you choose a different direction, you can also get a Y class or Y diamond. So these are different decoupling techniques. You can read more about the theory and performance of different decoupling techniques compared to each other in this nice paper. But here we choose XY4, which is quite reliable for superconducting technologies. All right, so this part is basically our mitigation.
Sure.
In order to develop it, we just have to continue to flip it. Is that the case?
Well, you don't flip it actually. Suppose you want to keep it at the same state. Yeah? This only fights against the environment. So environment, imagine, is sending random pulses to your qubit. It will be an electromagnetic environment. And you add a little bit of coherence for periodic counting and compute with the environment. You actually want to protect the state of the qubit as if it is, there is no environment on it. So you just want to kill the environment. So it's like order versus chaos. Right. So you execute the system with this error mitigation, and even with this error mitigation and optimization. So we can use everything in our hands to get the best result possible. Yeah? And you can see after even, let's say, 5 or 6 qubits, we no longer have even a 4 or 5 qubit GSA state. Yeah? So this is the situation of quantum computing. Yeah? So we shouldn't give false hopes. So we did some sophisticated error mitigation to some extent, some system default optimization of the circuit, but still we cannot even get 20 qubit GSA state. And you know, time is a resource for future optimization problems, quantum computing applications, or industrial scale, or even utility scale applications. So you want to get this one like this. Yeah? So there is a big road, long way to Ferrari, but it is fun to walk on it. And there is a lot of room for progress for young people. Yeah? So how you can improve it? So forget about system, follow your suggestions for connectivities, for instance. Maybe you can get somewhere like this.
There's a question. You don't do the error correction because of the 15 qubits you have? You do the error mitigation stuff, error correction?
Yeah, this is again, these 2 points can be improved. First, the optimization can be improved by tuning specific hardware with specific materials for this GSA generation. Then in the second, in addition to dynamical decoupling, you add further error correction. Then you can see this gets better and better. Yeah? There is a competition to produce larger and larger n-time mistakes. Well, in photons, so the situation is also somewhat different. Okay, so I want to give a homework. Okay. All right. So this of course I didn't tell you how long will it take to get this result of 100 qubits. I think it will take too long time. So even this well state, you were in like a waiting queue for 3 hours. Yeah. So you can try to run this on this real quantum hardware. But I suggest in somewhere, let's also do this on a simulator. Yeah? So like in the best state case, just use the IR simulator, for instance, or some fake backend to do this, repeat this simply code, but just execution stage, you change it to some simulator and fake backend to see how you get these results. Yeah? So then you should see some improvements definitely. Okay. So let's say now go to some quantum algorithm. Okay, third time is a charm. I would like to invite my technical assistant again. Okay, so there are very few algorithms which promise quantum speed up or advantages in time. And Grover's algorithm is one of them. It promises that our search can be very efficient. So there are, of course, some easy searches in classical sense as well, if you know somewhat about the database. Yeah? If you know some relations or order, which is called structured data. But let's assume we have no idea about the data set and it can be unstructured, so we have no clue. In this case, it is a difficult problem. That is why the Grover's idea offers some help. So in the classical sense, if you have this kind of unknown unstructured database, you have to make some number of trials that scales with the number of the elements in the set. But if you do some infinite quantum parallelism offered by quantum superpositions, which is at the core of the Grover's idea, you can get the quadratic speedup. Okay? So this may not be as exciting sound as maybe exponential speedup, but still, as you go larger and larger data, this is still a good promising result. So in the Grover search, I think you had this maybe today heard in quantum algorithms lecture also, sorry for if I'm repeating, but there are two basic ingredients. One of them is the oracle, the other one is amplitude amplification. Okay? Oracle is basically somebody or something that knows all. Yeah? So in our country, we have a lot of some ruins and relics and so on. Okay, so from Romans and Greece, also in Egypt and other cultures, we can find oracles are very respectful persons that are received a lot of respect because they are all-knowing. They have some close connection with the God, but they are not as close maybe as prophets. But still, they can give you some hints, some puzzled expressions to guide you in your search. So, one of the famous company Oracle also. So basically, this Oracle is somewhat related to search or quest. Well, for us, the definition of Oracle will be a quantum gate that marks the target state by simply flipping its amplitude. Okay? So remember, in quantum mechanics, according to Born interpretation, we have probability amplitudes. If you take your absolute square, they will give you some frequency or chance to get this outcome of your quantum experiment. Okay? So what this oracle does is it changes basically the sign of this amplitude from positive to minus or minus to positive. But we also teach in our quantum mechanics courses, global phase is not important. It is difficult to observe. So how this little change can help in a search mechanism? Mathematically, we have some set of states. Okay? So whenever the state is marked, it is amplitude disturbed. Okay? At this stage, oracle per se by itself is not much help to increase the speed of a search operation. Okay? So for instance, if you go to 2 qubits, oracle only marks the state 1, let's say you can choose another one by changing it this sign. But how to find this sign is not easy. Okay, but at least we can say that in the case of 2 qubits, I can use not control X, but control Z gate to map this problem, which is my first step in quantum programming, to a quantum environment by simply using a CZ operator. Okay? So whenever the first control qubit is 0, it will not introduce a phase flip. Whenever the control qubit is 1, it will make a phase flip. Okay? All right. So, to write it, first of all, as I said, the advantage of the Grover search comes from this quantum superposition. Basically, you search simultaneously if your different basis state or computational basis state 0, 0, 0, 1, 1, 0, etc. If they all match the mark state. Yeah? So instead of looking one by one, you simultaneously ask oracle and then hope for an answer. Okay, so therefore, we need to put this time not one state, like in the bad state, but 2 Hadamard gates to generate the superposition of 2 qubit states in 4 different basis combinations. Okay? And CZ gate is used by the student connected by line. Okay, this is the control, this is the to the flipped state fluid. Okay. So these two lines are basically for latent purposes. We are going to introduce them as classical registers, because after measurement, our quantum state vectors collapse to classical results, and therefore we need this classical data output. Okay, so this state is now familiar to you, that we construct this time a 2-qubit state circuit, but also with 2 classical registers. Okay. Then we add our gates. Sometimes you can also combine this state in a single line. We can write H0, 1 to combine these two in a single line, but you can also write 1 by 1. It's a small circuit. And here, control Z gate with control qubit and target qubit is appended. Okay. And this is the result of this draw. And for simulator, instead of a real computer, we use IR simulator. And it is primitive, this time will be a state vector simulator, so that we will be able to analyze the state vector output by it. Okay. And the result will be, after running the circuit, will be stored in the result. And we will see the state vector output from this result values, and we will print it. And when you print it, you will see that now we have a superposition of 4 basis states, 0, 0, 0, 1, 1, 0, 1, 1, with equal probabilities. And here, because of the control Z, the 1, 1 state has a facelift, minus sign in front. So the circuit is tested, it works properly. Now, we need an operator for amplitude amplification as well. So this is our state that we have just generated after the other gates. Okay. Then we do a facelift to this state. How to interpret this grammatically? Okay. Remember, this is our marked state, that is why we flip it this face using the oracle operator, CZ. Okay. And the effect of oracle simply grammatically is to reflect this state around the state which is perpendicular to our marked state and bring it to here. Okay? So this is basically, if you choose 1, 1 like your Z direction, yes? So this Z direction is close to negative Z direction. It's a reflection. Okay? And we can make an axis, like Y-axis. We can find a perpendicular state to define the y-axis relative to our marked state. And if you write, for instance, this state here, it is that product, scalar product with this 1, 1 is 0. So these two are perpendicular. And this is the perfect reflection around this line. Okay? So what we need is, we need to bring this state closer to marked state after the amplitude amplification. Amplitude amplification means the projection of the outcome of the Grover circuit should have a component along the marked state which is larger than the initial state. So this is amplitude amplification. And it is expected that if you run and run again this circuit, it will get closer and closer to the marked state. So we propose that this reflection operator can do the job. Why it does the job? Let's go to more simple geometry. So this is our marked state. This is after the oracle. Okay? And we want to bring it closer to this state. So we can get the reflection around the superposition state after the other gates, initial state. Okay? And we know that it will be closer to the target. And how to find this reflection? Okay? Let's say this is our state vector B, and this is its component perpendicular to initial state in the direction of A, and component of B in the direction of the initial state is A. So B is equal to A plus C. Okay? And remember, A is my initial state. If I subtract 2 times A and B from each other, I get A minus C. Okay? But A minus C is simply what I want. And it is the simply reflection of this vector B relative to initial state. So with this design, we can propose this operator, also called the diffusion operator, that will bring my initial state after Oracle transformation closer with higher amplitude along the direction of the mark state. Okay? This is the logic behind the grower. Okay, so at this stage, let's give some. Since using these geometrical arguments, you can assume instead of 2 qubits, these ideas actually work independent of number of qubits. So you can generalize the geometrical arguments to n qubits. You can, if you don't want to solve this mathematically, you can always Google it, but it's a nice proof of quantum advantage in 1 or 2 pages, just to show that there's a theoretical quantum advantage in the Grover search, which is quadratic speed up. Okay. Okay. Now I want to change this. I want to map in my first step again. Actually, my first step in my quantum programming. I want to map this diffusion operator also to a quantum circuit using available gates. Okay. So let me first give you the result. So 2 Hadamard gates, single qubit phase split operation, control Z and Hadamard. Again, this is a very clever trick. So we can realize that basically to get a reflection for an arbitrary direction, we make a simple fold of the state around this direction. Yeah? But this is complicated. How can I make it easy? First of all, this quanticity is complicated. Let's get back to initial state 0, 0. It is reset every qubit back to 0, 0. Okay? So you can show that if you apply Hadamard again, it will bring back to the original state. Okay? So therefore, we apply Hadamard gate to each qubit to bring back them to 0, 0 state. Why it is nice? Because you can find easily orthogonal states to 0, 0 states. And orthogonal states are easy to reflect. Yeah? Arbitrary states are complicated to reflect, but orthogonal states are easy to reflect. You just make a sign change. Yes, in the direction, it goes to -7. Okay, so this is what this, yeah, so you get 0 states, and you change the signs to reflect them. Okay? But I want to reflect my original state. Okay? So again, here, this is the original state as 0, 0, 0, 1, 1, 0. Okay? So this works for single qubit reflections, but 0, 0, and 1, 1, they have 2 qubit reflections, and therefore instead of single ZZ gate, you need control Z gate here. Okay? So that you can also change the sign of 1, 1. Okay? And finally, you reverse back the original state. Okay? So remove the effect of this initial Hadamard gates, apply Hadamard gates once more. And then you can use it to the algebra to show that this really develops the desired diffusion operator. Okay. So the full Grover circuit will prepare full supervision state for simultaneous search. Ask the oracle the mark state, then diffuse the information, and repeat it. Well, for 2 qubit case, actually it will be very, very successful. You can mathematically prove that it will, you only operate it once, and it will give you the result perfectly. Okay? Again, this is we just need to state simulation here because this will give us exact result, and also it is very simple. So we just use quantum circuit again with 2 outcomes in classical registers, and we add our Hadamard gates to prepare initial state, add the oracle CZ, and this part is for the diffusion operator. Okay? So we have Hadamard gate. I now this time use shorthand notation. Hadamard gate applied to 0 and the first qubit, so these 2. Okay. And same for CZ 0 and 1. and 0 and 1. This 0 and 1 means it's control and target, so therefore there is no square brackets, only normal brackets. But this 0 and 1 means it's an array, so it applies on array this operation z of 0, 0, 1. Okay? And we just see everything is correctly implemented by drawing. And here we also said that we're going to use IR simulator. Okay? And the second part of the step 1 is to find observables. In this case, our observables will be measurement outcomes. Okay? So we just want to see a single outcome, which will be our target state. And we simply add this measurements as the measure comment in QSIT and give where the measure qubit is and where the register is. Okay, so this is the zero and this is the first. Then we draw our circle.
Hocam, may I ask a question?
Yes.
Our oracle now flips 1, 1 to minus 1, 1.
Yes.
If we want to flip versus 0, 1 to minus 0, 1, how would we implement the oracle? And
Yeah, you have to find from scratch what should be the operator for this case. So this is if you want to map a classical problem, like you're looking for one thing among 4 items, then you can always say, okay, this classical item maps to my 1, 1 state. So usually it is better to go in the reverse direction. There should be, this is what available gate is. If you can find, for some reason, 0, 1 is needed, you should find another gate for it. Okay, again, this time we use the same type of structure for the state vector analysis. Remember last time it gave us superposition of 4 computational basis states of 2 qubits. But this time, if you assume this 10 to the minus 16 is 0, all the computational basis states are vanishing with vanishing amplitudes, but only the one with one remains. Yeah? So this is the major part, you can forget about it, but it gives us very good probability the desired 1, 1 state. And this is only for exact state vector result of the circuit. Okay? So if you do the experiment, if you run your circuit on the simulator, just evolve it in time. Okay? So let's say we run it 1024 times, and it always gives us the result 1, 1. Yeah? So this is how exact the method is. And these comments are very standard. So again, you can here change the number of runs by adding the shots. Okay? So if you add this option shots is equal to 1, of course you get again single shot result. Okay? So this is a single shot result for 2 qubits. And you can check what happens if you go to 3 or more qubits. So this is my homework actually. You can try to go and analyze this calculation to 3 or 4 qubits in any way you like. And you can also look at this more general documentation, which is given in QSIT documentation. It is a little bit more complicated than necessary, I think, but you can still look at it because they are using some built-in functions. In QSIT, there is a Grover operator directly you can use, and this is just introduction of this Grover operator. You just look at the inside of this operator in this example. Okay, so you can try to see this quadratic scaling also as you go more and more qubits, how the time is. Number of runs and shots is changing for the same success rate, and you can see and get a feeling of quadratic advantage in quantum algorithm. All right, so this is all I want to say. Hopefully, this was some introduction that you can build from here, and thank you for your attention. Any questions and comments are welcome.
Can you hear me?
Oh, it's a different person. We should, we can give, of course, we can take questions.
Hocam,
Yes.
indeed, I don't have a question, but I have a request from you. Is there any possibility that you can share with us presentations? Because due to technical problems, then we cannot hear the voice of the speaker so clearly from the Zoom. So if it is possible to share with us the presentations, it will be so beneficial for us.
Yeah, of course. You will also see the homeworks. Yes, so I will share you these presentations, of course, with the help of our organizers. Yeah, definitely. And I think we can do this today so that when you go back home this evening, you have something to do.
Okay. Thank you, hocam.
You're welcome. Yes, sorry.
The quantum computers has the limit of having 127 qubits currently, and this is a hard limit for us to that limits us, right? I mean, if we are to want a simulation that runs on 100 million bits just to see the speed increase, can we do that?
Yeah, with simulator, of course, you can go higher number of qubits, but for real quantum computers, you cannot. But the problem is that, first of all, we should define what's a useful problem. Yeah, for instance, there was this Borealis photonic computer, which solved this Galton board problem. Basically, if you go to a science museum, they drop some little marbles and then they distribute in a binomial distribution, yes, by hitting some little rods. But if you don't see the board, and if you're just given an arbitrary distribution, can you guess the board? This is known as Galton board problem, and it is generalization, and it's a non-polynomial hard problem. And a quantum computer with a large number of qubits can solve it, but you cannot make money out of this. So it's not industrially relevant question. So if you can find some in the utility area, some kind of thing that you can do with 100 qubits or 150 qubits, that is what people are after currently. Yeah.
With if you use the distributor, you can do up to maybe 40-50 qubits, right? And you have to use a quantum computer.
Yeah, of course. So with hundreds qubits, you still have to use a real computer. Well, photonic computing offers advantages. If you go to another web page, you can send them an email and ask access to photonic computers also. And you can see they have different approach to computing called continuous variable quantum computing. They have nonlinear optic gates, squeezing gates, and different optical interferometers. We will have some courses here by Uğur Hoca on nonlinear optics. So if you learn these things, if you learn quantum optics and nonlinear optics together, then you will be at a level which you can understand alternative approaches to quantum computing. And measurement-based quantum computing is also another approach. So these are a little bit more advanced and promising, perhaps to go to higher number of qubits, because environment is a big problem for superconducting architectures, also for ion traps. But for photons, it is not the environment, but more interactions between the photons are not very strong. This is the main problem. So they have different problems, but promising architectures are coming. Yes, please.
Can you elaborate a bit more on what distance means for qubits in n-dimensional GH that taken down?
Yeah, it is basically actually the size of the state. So this distance interpretation is meaningful in my original map on a linear chain. But if you go to a real architecture, you can only hope that maybe first 2 qubits or 3 qubits will be given at an equal distance on a triangular lattice or square lattice. Only after a certain number of qubits you will see distance effects, and maybe this decrease will be not monotonic and so on. So here distance is vaguely defined only on a linear chain.
Well, but isn't the linear chain just a representation of what's actually going on? So, or are we just actually talking about physical distance?
No, this is on the linear chain, the correlation between the first qubit and the, let's say, the end qubit, yeah, the end of the chain. So saying this is a distance is meaningful only if you have a line distribution of the chains, of the qubits on a chain. In actual hardware, this is not properly correct, rigorously correct. So it's better to say the size of the state, actually.
Okay. Could phase kickback be an example of distance, for example?
Sorry?
Could phase kickback be an example of an effect that goes, that affects less as more controlled qubits are, more targeted qubits are?
Yeah, this could be an example to that. Yeah. But here the actual, so the distance, you don't need to call it as distance. Normally, the robustness of the quantum state becomes more and more fragile as you go to larger quantum state. It's more fundamental fact than actually even environment. It is very, yeah, the phase of, you can go, for instance, trapped ion quantum computers or superfluids, where you have this Mexican heart shape type of potentials, yes. So what happens in nature is actually, whenever you break some symmetry, right, then the nature tries to recover it. So actually, so you're always on the top of an unstable equilibrium. If you fall it from here to somewhere, you break the symmetry, yes. But then this state even will decrease in time, even if there is no environment. Yeah, so this what happened in Bose-Einstein condensate, why it has a finite lifetime, because it breaks this phase symmetry. Yes, because the phase angle, so you have a homogeneous 2 pi distribution. Yes, if you break it by choosing a special coherence, which is a Bose-Einstein condensate is all about. Yes, if you have some phase coherence, eventually this is going to be destroyed even if there is no environment. And even if you isolate the environment, this states will collapse. But hopefully they will live long enough to do something useful. This is the main motivation.